you, Jacques, for the introduction. So just to be clear, this is not a talk about equality in type theory, which is something that I really know far less about than many people in the room. But this is a talk about equality. And it's a talk, when I give talks in like maths departments, I normally make fun of computer scientists. Now I'm giving a talk in a room that has many people with computer science backgrounds, and so I'm going to lay into mathematicians. And the problem, one of the reasons that I'm in this area in the first place is that I have perceived some kind of degeneration in the way mathematicians speak about equality. In the papers that I was reading before I moved into this area, papers to do with the Langlands program. And I'm just highlighting the fact that the degeneration is problematic because I want to talk about, I want to formalise modern number theory. That's exactly why I'm here. And then I can't formalise modern number theory if people are people are writing things that aren't true. It's sort of difficult to work out. So brief history of equality. So first of all, people use A equals B, 2 add 2 equals 4. You use A equals to mean that two numbers are equal. Back in the days when there were sets of numbers, like the real numbers, but people weren't specifically interested in comparing sets of numbers, they were interested in numbers. So historically, equality means that two numbers are equal, and then of course, when we started arguing more conceptually, you can start using it to mean that two sets are equal, and we know what it means for two sets. There's an axiom that tells you when two sets are equal. Two sets are equal when they've got the same elements. So this is again a completely unambiguous concept of equality. And then the problems start arising, and this talk is just really sort of some screenshots of papers that I've had to read in my life. So then they start using it to mean, well, they might not be equal, but they're the same, right? In the sense of univalent mathematics, they're the same in an extremely strong sense, but they don't actually have the same elements. And that is actually not really, as the univalent people will tell you, that is not actually a problematic usage of equality. That's not really what this talk is about. But the problem is what happens after that, when you start saying actually there's this idea of things being canonically isomorphic, where you're admitting that they're not equal, but you're adjoining this extra adjective that says they're not equal, but it doesn't matter because they're canonically isomorphic. And this is a word which I argue constantly. It doesn't actually have a meaning, or maybe it has a disputed meaning, or maybe it has more than one meaning. But unfortunately, this is the word that we see throughout the mathematical literature. Even not in papers written by people who don't know what they're talking about either. This is a word that sort of permeates the literature nowadays. I'll give you some kind of examples of why I think this might have happened, and then we kind of move on from canonical isomorphisms to canonical homomorphisms, so this really happened. I got into trouble with this. So in 2021. There was somebody giving a talk on the Langlands program in the London number theory seminar, and the usual thing in the Langlands program, they have a bunch of pies which come from analysis, and they have a bunch of rows that come from algebra, and they have a construction. They're given a pie after a huge amount of work and makes a row, and they explain this construction, and then they wrote theorem. This construction is canonical. And they were stating the so the theorem, one said it had some property, and then part 2 said it was canonical, and then part 3 was something else. And I objected to this in the middle of the seminar. I objected that this was a completely sort of contemporary, meaningless statement. And they said they guaranteed that they could prove that the construction was canonical. So I started saying that it had no meaning, and then the person who ran the seminar basically had to tell me to shut up. So we agreed to reconvene down the pub afterwards, where they were going to tell me what the heck they meant by, one of the main theorems in their talk was what I perceived as a completely content-free and meaningless assertion. So they assured me that down the pub they would explain to me why their construction was canonical. And of course we went down the pub and I asked them about it, and we never got to the bottom of it and started talking about it. So, as far as I'm concerned, this is a meaningless set. And that was really what pushed me over the edge. That you could say this in front of a room of number theory, some of whom were very prestigious, and that you could get away with it, and I was the only person that wanted to object. So I'm going to spend 30 minutes or 25 minutes just whinging. Whinging is a good English word, I mean complaining. I'm going to spend 30 minutes complaining about mathematicians. So I'm not going to go on about the basics, because we all know the basics, so you can start, we all know that 2 add 2 is 4, and then there's this idea that A and B are equal if they're uniquely isomorphic to each other. For example, if they satisfy the same universal property, because an arrow theoretic argument shows that if 2 things satisfy the same universal property, then there's unique maps from each one to the other one, and they're composites of the identity. Okay, so the point is that mathematicians might say that these things are equal, but they're not actually equal, they're just both doing the same job. And there's slide 1, this is Grothendieck. Grothendieck wrote these volumes of algebraic geometry starting in about 1960, and this is the EGA1 up to EGA4 and SGA1 up to SGA7. These all got published in this 10-year period between 1960 and 1970, where Paris was like the place in the world to be doing algebraic geometry, and all the top people were there. And this is this is one of the first pages. This is section 1.3 of EGA1. And so this is how, and this is the fundamental construction. So in EGA, there's an EGA0, which is ring theoretic background, and in EGA0 they've explained a bunch of ring theory. And now we're in EGA1, so we're doing this new thing called a scheme. And we're about to make a definition of something to do with schemes. But the point is here that we've got a ring A. This is a commutative ring, and we've got a module A. So A could be a field, and then M is a vector space over A. And the dubious thing that we have here is that we have this MF equals MG. So this is there are early examples. There are examples in Bourbaki of this word canonical. But we have MF equals MG, and this is not true, right? M localized at F. So we've got M localized at F equals M localized at G. Right? And M localized at F is formally, if you read EGA again and find out what the definition of this is formally speaking, M localized at F is M cross the set 1F squared. This is numerators, and we're dividing by F. This is the idea. M has got elements called little m, and M over F has got elements called little m over F cubed. That's the difference between M and M localized at F. So you're allowed to divide by F. So formally, M localized at F is a pair consisting of a numerator and a denominator, and then you've got the issue that F divided by F is 1. Right? So there's some kind of equivalence relation. And if you believe in set theory, then you think that M localized at F is the set of equivalence classes of so it's an element of M localized at F is a subset of this, consisting of equivalent things. But similarly, an element of M localized at G is M cross a bunch of powers of G. So these things are not equal, they're subsets of different sets. And they're not equal. The argument that they're equal is that
just about the lemma, s'identifie canoniquement.
Yeah, exactly. So this is the issue. There. So the point is that MF is not equal to MG, but MF is canonically identified with that thing there. Right? So this is canonically identified with something that he calls S primed F inverse of M. And this lemma 1.3.2 shows that under these hypotheses here, if df equals dg, then SF inverse primed of M, that really does equal SGF primed of M, right? So those things really are equal, right? Unambiguously equal. And then the point is, and then MG, we are assured that MG is canonically identified with this. Right? So that's the proof that these things are equal. These things are actually equal, and these things can be canonically identified. And there's no definition of the word, there's definitions of localizations in EGA, but there's no definition of the word canonical. So that's what we have. And now the question is this the end of the world? Right? Because now, okay, so equals is now being used to mean things that are not equal, but is this the end of the world? And in this, hello?
Question.
Yeah, go on.
Why isn't this an example of the thing you said before was unproblematic when you have a universal property?
Yeah.
And then these things are canonically identified because there's a unique.
Yeah, exactly.
That's fine.
Yeah, this is fine.
You already said
This is the
that.
beginning of the problem.
But now you're complaining, but a minute ago.
I'm not complaining, yeah, I'm saying that actually we're going to get worse, right? That's case study 1, and I'm going to say that they're not actually equal, but actually here it's probably not a problem. Okay, and for exactly the same reasons you say. Because not only, the point is that they both satisfy, they both satisfy universal property, and there is indeed a unique R-modular map between them that does a job, and similarly for the rings, these rings R, F and RG, they're not equal, but they are uniquely isomorphic as R algebras, and they all, they satisfy unique properties. So if you're in the univalent world, right, if you believe in the univalence axiom, then indeed they are equal, right? And univalence doesn't make mathematics collapse. So
you're kind of saying that using the word canonical here is okay because there's a unique map?
yeah,
But
there's some implicit, Grothendieck knows that there are unique, obvious maps in both directions.
doesn't it mean that there is a way that is standard to obtain such a map from the inclusion?
Yeah.
Whether it's unique or not doesn't matter. If you're saying, I mean, I don't know in the rest of your examples, but is it referring to an implicit construction that everyone's supposed to know about?
There's an implicit function that goes in both directions.
Sure, but there is also an implicit function that comes from just the inclusion, even when it's not, even when df is not equal to dg. There's not a unique map.
Yeah, there's restriction.
Yeah.
So there's all the when you see these things, there's obviously maps between them, and you can't do tricks like, oh no, what if you replace it by a minus? Like you can't send AF to AG, but then throw in a minus sign, right? That's the kind of thing that might throw you off, because maps of rings must send 1 to 1. And this thing, both of these contain, I mean, they don't contain M. There's a natural map from M to both of them. If you want a map from AF to MG that commutes with the action of, with the M's living in both of them, then there's only one. So this is not that. But so the problem with this is that Grothendieck is doing it, and the people who are reading Grothendieck don't understand it properly. And he's using the word canonical to mean there is only one possible way of doing this, and we're going to do it that way. So there's a unique, these R algebra maps are unique, they're uniquely isomorphic, and morphism of rings send 1 to 1, which really rigidifies things. So what about morphisms of additive abelian groups, when you have this extra possibility? So, okay, so here's case study 2, and it's the Stacks project. And the Stacks project is a much more important thing than EGA. And the reason it's much more important is because although EGA was sort of the foundational material that started everything, and it's the Bible, the thing about the Stacks project is it's free and open source and on the internet. So when you get students who want to learn algebraic geometry, they don't go to the library anymore. They just go to the Stacks project because it's there and it's easy to get, or Vakil's book, anything that's free, and that's what kids are reading, right? They either steal stuff or they read free stuff. And so I just noticed that my PhD students just learn algebraic geometry from the Stacks project. So what it says in the Stacks project is really important, much more important than what it says in EGA, because no one's really looking at EGA anymore. So this is widely used by PhD students, for example, my PhD students that learn algebraic geometry. And this is one of the fundamental results of the Stacks project. This is computing the cohomology of projective space. So Q, N, and D are natural numbers, and all of the rest is just sort of garbage, right? R is a ring, and Pn is projective n space, but it's a scheme you can make from the number n. And then and this is a sheaf on it, and this is the cohomology. But at the end of the day, you have a commutative ring R and 3 natural numbers n, and then you're making an abelian group. Okay, and this abelian group is a cohomology group, and so if you look at the formal definition, it's either defined as, it's a derived functor, and so then you don't really have a definition, you just know the universal property, or there are concrete definitions in the form that you write down these things and they're called Q cocycles, and you write down this subset of things and they're called the Q coboundaries, and you quotient out the one by the other, and you get the cohomology. Right? So formally, the definition of this is Q cocycles divided by Q coboundaries. And now the claim is that this cohomology, this fundamental calculation, which is absolutely needed for Fermat's last theorem, because Langlands and Toll give you a modular form produced using harmonic analysis. So they give you a function on the upper half plane, and this can be manipulated until it becomes a section of a coherent, a section of a line bundle on a compact Riemann surface. And then you go from this compact Riemann surface to an algebraic variety defined using polynomial equations. And the miracle is that that holomorphic function is still there, and it's now defined by polynomial equations. And the proof that analytic and algebraic functions on a compact Riemann surface are the same goes via, you embed them into projective n space, and it goes via a divissage. And you prove that analytic functions and algebraic functions on projective n space are the same thing, and the crucial thing is you reduce it to a calculation of these dimensions. So this is the absolutely crucial part of Serre's Gaga, which is needed everywhere. It's the link from complex manifolds to algebraic geometry. So computing the dimension of these spaces is really important, and we do more than compute the dimension of these spaces here, according to the stats project. We even compute what these spaces are equal to, right? And these spaces, for example, all of those spaces, if you don't satisfy these equalities, all of those spaces are equal to 0, and in particular equal to each other. But they're clearly not, right? Because but when you say equals 0, that's code for I have one element, right? That's how you can interpret a cohomology group equals 0. That just means I have one element. But these ones here, and especially this one, this is a load of old nonsense. This is the thing, right? Whatever this says, if Q equals n, so this is the top cohomology group, if Q equals n, then this thing here is without a doubt Q co-cycle. So it's if you like, it's a limit, it's a co-limit over all open affine covers of some big collection of Q co-cycles divided by a big collection of Q co-boundaries. And so how the heck can we justify the claim that it's equal to some random abelian group? And the answer is, well, you don't just take some co-limit, you take a carefully chosen cover of projective space by outliners. And then you don't use all co-cycles, you only use alternating co-cycles, because it's a theorem that cohomology group doesn't change if you completely change the way you're calculating it. It doesn't change up to canonical isomorphism or something. And so then you do this calculation involving this careful collection where you use n plus 1 open sets, and you work out the alternating co-cycles. And when you do that specific calculation to work out the cohomology group, it turns out that the Q co-cycles are functions from the one element sets to this ring, to this group. And the Q co-boundaries are 0. And so obviously, functions from the one element set to this modulo the 0 function are obviously equal to this, and so we get this equality. And so for me, that I'm quite uncomfortable about that. So here's a question that one could ask. If you take this projective n space, this has got coordinates, this is like r to the n, but it's some compactified r to the n. You could just, what happens if you just swap the first two coordinates? When you swap the first two coordinates, this messes up this messes up your calculation of your alternating cohomology groups, because you introduce some minus 1 to the n somewhere. And then the question is, do we ever get the minus 1 to the n introduced somewhere else when you swap those two coordinates? So if I take the automorphism of Pn that swaps these first two coordinates, then obviously I still get the same thing here, but does this equality, is there a minus sign introduced or not? Right? And this theorem here, this lemma, there's no way that we can work out the answer to that question just by staring at the lemma. What happens when you change? What happens when you apply a permutation matrix to Pn? Do you end up with a sign of the permutation or not? And the answer is we don't know, because what this equals really means is they can give you a map, right? And there's a formula for that map, but they haven't written down the formula. This is a definition, but it's been presented as a theorem because mathematicians have forgotten what constructivism is. And they're convinced that the thing that they're doing is proving theorems. And so what's happening here is that they're writing down a map. And they're writing down a map, and they feel it's such a natural map because they never had to make arbitrary choices. They never had to pick a basis or anything. They wrote out a completely natural map, and it was so natural that they're convinced that nothing happened, and so these things must have been equal. I think that's what's sort of happening. Whereas in fact what's happening is they're making a definition, but they don't know that they're making a definition because they've lost track of the difference between these groups are isomorphic and this function is an isomorphism. So there's me, there you go, I've said this. So a cohomology group is a quotient of a cosine by cone boundaries. And I asked Brian Conrad what the hell was going on in this paper. He said the idea is there's only one sensible way to compute that cohomology group. And when you compute it in the one sensible way, that's what you get. That's his explanation. Hello.
And do they ever use this way to compute the cohomology?
They use the dimension.
They don't use the map.
No, I mean, no, they don't even write down the map, so it can't be important. they need the dimension. That's the crucial thing in the proof of Guy. And then the dimension is fine. Now, when we form, I mean, the question is, we don't know it because we haven't formalised it, right? When we formalise it, that's when we're going to find out. So this is the Wikipedia. This is the current state of Wikipedia's article on canonical maps. Canonical map is a map between objects that arises naturally. So this is exactly, you're trying to explain a vague word. Let me just explain it using another vague. It arises naturally from the definitional construction. So this is Wikipedia today, right? Or yesterday. Often it's the map which preserves the widest amount of structure. Right? Often, not always. And there you go. And a choice of canonical maps. Sometimes this is a dangerous statement because I've been going around asking mathematicians, can you have a choice of canonical maps? Or if they're given two objects, is the number of canonical maps between them at most one by definition? That's or possibly, or maybe it depends on a convention. So there you go. So that's what we have to work with when we move. So now we're moving away from the concept of things being equal to things being canonically isomorphic.
But here you're basically, in your argument, confusing normative as how it should be, with empirical as a natural or social science of mathematics, where they try to describe what they're seeing.
The function that we found, exactly, as opposed to the function that God gave us, and that might be the negative of the one that we found. So, I was just talking about sheaf cohomology. That's these cohomology groups, these quotients of cycles over boundaries. And to prepare for this talk, I thought I'd go back and look at the definition, not least because I'm at some algebra geometry conference next week where we're formalising stuff in Lynn. So I thought I should read the definition of sheaf cohomology. And so here we are. This is EGA 3, where they do cohomology. This is literally section 1, subsection 1.1, subsection 1.1.1. So this is the very beginning of EGA 3. This is what I decided to make sense of. So A is a ring, and F is a collection of R elements of A. And so I thought I would do the special case. So let's do two, it's F and G, right? Let's do R equals 2 and try and work out what Grothendieck is. And we're even before we get to cohomology groups of schemes, we're going to do causal complexes. Okay? And what's going on this page here is that they define a complex is lots and lots of maps between abelian groups, and if you do two consecutive maps, you get 0. So here's a complex here, and it's lots and lots of zeros there, and then there's an A and an A. A can just be the real. If you don't know what a ring is, A is the real numbers, right? So there we've got a complex that looks like this, and these terms are indexed by the integers, and this is 0 and this is 1, and then this is -1 and this is 2. And this is multiplication by F. So there, that's what this is, this chain complex K dot of F. It looks like that. So it's two non-zero vector spaces, and the map between them is multiplication. And complex just means if you do two consecutive maps, you get 0. So if you start here and then you multiply by F, and then you send everything to 0, you get 0. And similarly, if you start here, then you're at 0, so now you're at 0, and you multiply by F, you get 0. So any two maps, you get 0. So there we go. So there's a complex. And there's another complex as well that has A multiplication by G. So we've got these two complexes, and then we take the tensor product of these complexes. Okay, now we have to work out, so now somehow, okay, so I'm going to take the tensor product of these complexes. So this is this first complex, it's going to look like this. It's going to be A tensor A, and then A tensor A. And then, so now we've got a big infinite square. A tensor A and A tensor A. There. and now we're going to get a double complex, but there's somehow, we're supposed to have a complex, and so now we add these up here, and that's going to be, we're going to collapse the double complex to a single complex, and we're going to have a complex in with 3 non-zero terms, and we're going to make the maps, and they're all going to, and this is going to be F, and this is going to be G, and this is going to be F, and this is going to be G. So you do this calculation. I was doing this calculation in my hotel room 2 days ago. I've got this A plus A to A. We've got these maps here, and when you do this one and then this one, you get 0. And I'm trying to work out what this is, this definition of this product of complexes. And so I figured that it must be, this map here must say x goes to the vector fx gx there. And then this map here must send AB to, it's going to be kind of GA minus FB, GA plus FB. This is the naive, if you just look at all these, we've got multiplication by F and multiplication by B, you've got to put them together to make some kind of picture. And you do this, and you try it, and it doesn't work. Because you start with X, and you go to FX, GX, and then you do GA, so we start with X here, you do it twice, you're supposed to get 0, and X, you get, so I get GFX plus FGX. If I do it this naive way I've written it down, where you just throw in, you just take this naive tensor product of complexes. So this can't be, so somewhere I've made a mistake, because this tensor product complex is supposed to be a complex, which means if I do a map and then another map, I get 0. And I've done a map, I started at X, I've done a map and I've done another map, and I've got GFX plus FGX. And of course, the mistake I must have made is I've got sign wrong. Right? If it was GFX minus FGX, then something would cancel. So I know that I've made a sign error, and the reason, and so there's I either put a minus there, or I put it there, or I put it there, or I put it there. And I put exactly one of those 4 places, and I fixed the problem. Or 3. I need to change an odd number of those pluses to minuses, and then I'm doing the right. So I had a look. So now, of course, I've got to work out what's going on. So he gives a reference. So this is Gaudemond's book on sheaf theory that had come out 2 years earlier. And I looked up. I didn't have access to Conrad's book on sheaf theory. I couldn't find a free copy online. So I had no idea which one of these signs. So I can't read anymore EGA3 because I don't know which sign is wrong. But what I do know is that you do the natural thing and it really doesn't work, then you have to make some decision about which signs you're going to change. Okay? And it's very difficult to argue that there's a canonical way to do that. But for me, it's very difficult to argue that one of those symbols is more, especially if it's going to be one of these two. Like which one is it? So there's some kind of in the whole of cohomology. This is the beginning of the theory of sheaf cohomology. The beginning when the whole thing was invented. Right? There's some kind of convention going on, and there was this. At the time, it was quite funny. Like people didn't quite know what the convention. So Hausdorff wrote a maths book about duality, and he even says at some point in print that the later diagrams he didn't really check that if you went round that way and went round that way you got the same. There might be off by a sign, but it didn't matter. The joke, just working characteristic 2. That was the joke. So hilarious. So Brian Conrad, who's a very careful mathematician, attempted to work out what the heck was going on. So this is so Brian Conrad rewrote Hartshorne's book. There. So he argued that in the book there were unverified compatibilities, means that Hartshorne is claiming that some function equals some other function, but notes that actually it might be minus that. So most of them aren't hard to check, but some of them are genuinely difficult, he says, and they're truth dependent in an essential way on a correct choice of sign conventions. So I illegally downloaded. I do own Conrad's book, I can assure you, but I illegally downloaded it, and there it is. Section 1.3 sign conventions. So this is what Conrad has to say about signs. So there we go. So there's not too many signs here. That looks all right. Oh, there's a minus p there you might have to watch out with. Okay, so this is quite a long section. And then there's you have to be careful here because there's a plus n and a minus n there, but you have to, the issue is that, there we go, so now this is the first. He's tried to make some sensible choices of size, and now he's got some identification of two cohomology groups, but the problem is the equal sign here, that equal sign secretly means you multiply by some random sign. There you go. And he mentions that actually this really happens. So he cares about the case I equals 0, and then you get minus 1 to the n squared. And so you get minus 1 to the n. And so there we go. So now the book hasn't started yet. This is the thing we were just talking about. Tensor product of two, the dot means a complex. Tensor product of two complexes. And Brian's like, yes, that's what we're going to do. That's our convention. We're going to take one of these random things here, and we're going to change it by, there's a 50% chance that we'll add a minus sign. Right, this one we don't change, and this one we might change. So out of the 4 maps, 2 of them are not changing, and 2 of them is 50% chance. So for every commutative square, we're introducing one sign. And so now that makes all the diagrams commute. But we could have put it on that side, or we could have used minus 1 to the something else. When they're doing POMs, they use minus 1 to the n plus, n is p plus q. So that's another way of choosing a random number which is even or odd with probability 50. So there's a random choice, and there's a completely different random choice. And now, and that just goes on and on and on. So here's one consequence of Conrad's sign conventions, is that there's a cohomology group there, this fancy curly hom there. There's a hom, and actually when you think about it, that set there is equal. So those lines there mean that those are equal, right? Not just equal as there's univalence equal. This is like, actually they're the same thing. So those things are the same thing. Those things are the same thing. These maps here are both called alpha M, right? And they're both isomorphisms, and unfortunately, this diagram does not commute. Because you can't have all the diagrams commuting. So there's a warning in Conrad's text that sometimes you can replace something by something which is literally equal and introduce a minus sign. Okay? So there we go. And there's a 10-page section on sign conventions.
Is that in MathLib?
No, because you can't. So there we go. So page 17, here we go, acknowledgements. There. It is my belief that there are no mathematical errors in this book. That's how smart Brian Conrad thinks he is. After a literally 10-page exposition where he explains all the sign choices he's going to take. So there you go. So that's what, you can't make choices that make everything right. So there we go. So there's 13-page list of errata on his website. so that taught him. And every single one is either, oh, there's just a stupid typo, or oh, there's a sign error. Right? And this is the foundations of modern duality on which a lot of algebraic geometry is done. So it's really difficult to get right, and then I will just leave you with this. The point is that people don't care, right? They know the theorems, they don't care. But I won't talk about that, I'll just leave you with this last thing. So this is what happened. This is by the time we've got to the 60s, by the late 60s, is that people like the Langlands people have realised that you can say something's canonical and get away with it. And so now we just have some random cohomology group here, and the big theorem is that that cohomology group there, there's a canonical homomorphism into some other group, right? So this is just that theorem makes. This is Langlands. This theorem, as far as I'm concerned, makes no sense at all. It's not a theorem; it's a definition. There's a canonical homomorphism. These are both groups. They look fancy, but they're both abelian groups. So there's this involution, and Langlands proudly tells you what the kernel is. And you know what the kernel is, and that doesn't tell you, right? You can still put the minus sign and change the kernel. So we're supposed to formalise Langlands, so we're going to formalise that theorem there, but you can't work out what it says. And that's the problem we face, and that's the end of my talk.